All right, so what does all this mean? So good K-maps, which I made a copy of somewhere and I promptly lost. Oh, here they are. Okay. All right, so here's the K-maps I got from the truth table. And then you cover these things. So whoever gets to do S0 is lucky because you got some 2x2s, right? So this one over here, so we're looking at these two squares and these two squares. B1 could be a 0 or a 1. B0 has to be a 0. So that's B0 bar. A1 could be a 0 or a 1. A0 has to be a 1. So that's B0 bar A0. And then this one over here, B1 could be anything. B0 has to be a 1. A1 could be a 0 or 1. A0 has to be a 0. So that's A0 bar. So if you're doing a sum of products, it's this and it ORed with that. If you do a product of sums, this one's going to be fairly unpleasant. Well, you have a 4x4 here and you have a 4x4 on the corners. So it's still going to be two terms. And let's do that. Just for fun. So product of sums, you have this square in the middle, and so I'm just going to look up here. B1 can be anything. B0 has to be a 1. So I'm going to write B0 bar ORed with, and then A1 can change. A0 has to be a 1. So that's going to be A0 bar. And then this outer one, we just Pac-Man all four of those. And so in the corners, B1 can be anything. B0 has got to be 0. A1 could be 0 or 1. A0 has to be 0. So that's B0 or A0. And so here, this is S0. Right? We can FOIL these. So B0 bar ANDed with B0. That's the first. Here's the outers. Here's the inners. And here's the lasts. Well, what is X ANDed with not X? That's equal to 0. And A0 bar ANDed with A0 is 0, and 0 ORed with something is just something. So these two terms basically drop out, and you get B0 bar A0 or A0 bar B0. And that's exactly what we got when we did the sum of products. B0 bar A0 or A0 B0 bar. So you end up with the same equation sometimes. If you simplify them enough, they've got to be the same. And sometimes it's pretty straightforward to turn one into the other. In this case, just multiply out, cancel these terms. Sometimes it's not very easy to turn one into the other, but they should be the same thing. So S2 is not too bad. It's a 2x2 and then a couple of 1x2s, 2x1s. And S1 is kind of not really fun to do. You got a rectangle there, rectangle there. That's by itself, and then these you can overlap. And so it's 6 equations. So you do this and you come up with these simplified equations for S0 equals, S1 equals, S2 equals. So what have we done? We wrote a system diagram, we turned it into a truth table, and then we wrote K-maps for each of the outputs, wrote equations for those, and that gave us 3 equations. The next step, if you were going to build this, would be to design a circuit. For example, if I want S0 to be equal to the OR of these things, I could take A0, invert it. I could take B0. I could AND those. I could also take B0 and invert that. And I could take A0 uninverted. And I could AND those. And then put those through an OR gate. And there's S0. And you would probably do this with your inputs going vertically. Put an inverter next to each one so you have A0, A0 bar, A1, A1 bar, and so on. And then bring your lines across the way we did week 1. And you'd get your 3 outputs, S0, S1, S2. We'll come back to that in a while. So that gives you a circuit. And is this going to be a fun circuit to build? Probably not. Right? So S1 has got 6 product terms, and some of these have 4 expressions. Well, if you have 2 input AND gates, you got to use 3 of those to get a 4 input AND. So you got 3, 6, 8, 10, 12, 14 AND gates, and then you need to OR things to 3, 4, 5 OR gates. So that's 19 gates just to make S1. And it's all kind of, you hear the term random logic. It's not really random, but there's no easy pattern to see in this. So you got 19 gates, you got wires hooked up to all of them, and you test your circuit and it doesn't work, and it's kind of a pain. And that's just for S1. Then you got to do something for S0, and you got to do something for S2. And this is to make a 2-bit adder. It can go up to 3 plus 3. What if you wanted a 32-bit adder? Because most computers will add 32-bit integers. So how big is the truth table for a 32-bit binary adder? How many inputs do we have? 64 inputs, 32 bits for A, 32 bits for B. So your truth table is going to look something like this. A0, A1, A2, A31, B0, B1, B31. You got a total of 64 of these inputs. And how many outputs do you need? Let's just say 32 bits. So you got S31, S30, S29, S2, S1, S0. You got 32 bits there. So you have 32 equations. Each equation comes from a truth table with how many rows? 2 to the 64th. So how big is 2 to the 64th?
Very much.
It's pretty big.
At least 12.
At least 12. Excellent. So 2 to the 10th is about 1,000. 2 to the 20th is about 1,000,000. 2 to the 30th is 1 billion, a gig. 2 to the 40th is 10 to the 12th. 2 to the 50th is 10 to the 15th. 2 to the 60th is about 10 to the 18th. So that's 1 billion billion. That's just 2 to the 60th. So 2 to the 64th, 16 billion rows. And guess what? Half of those are going to be 1s for S0. So you're going to have 8 billion product terms that you need to feed into an 8 billion input OR gate. Okay, this is not how we design adders, obviously, because the whole universe would be repurposed to just making a single 32-bit adder. So there's got to be a better approach to this. So in Lab 3, you're going to go through the analysis you just did on the board. So remember what you did. Take pictures if you want. Because part of Lab 3 is going to be saying, let's build a 2-bit adder using this approach. Okay, you're going to make the truth table, system diagram, truth table, K-maps, write equations for simplified versions of S0, 1, 2. But then it's going to say, go ahead and implement your equation, possibly using what you know about adders. Okay, that's the part we're about to go over, this possibly using other design techniques. So we're going to introduce a new type of circuit, which is called a full adder. And this is going to make Lab 3 a whole lot easier to do. It's still a lot of work, but it's going to make it a lot easier. And here's the idea behind the full adder. Suppose I'm trying to add 4-bit numbers. We know how to do this. We learned how to do this in grade school. We take our first digit and our first digit, we add them together, we write down the sum. And if it generates a carry, we put the carry over here. The carry of 0 and 1 is just 0. And then we add our second digits together with whatever carry we had. 0, 1, and 1 is 2, right, which we write down as a 0 with a carry of 1. And 1, 1, 0 is 0 with a carry of 1, and so on. So this ends up being 1, 0, 0, 0, 1. And we didn't use this big, long truth table in our head. We didn't use these Boolean equations. We did something very simple. We operated 1 bit at a time. And we produced a sum and an outgoing carry. And then we added these 3 bits together, and we produced a sum and a carry. And then we added these 3 bits together, and added these 3 bits together. So what do we have to do? We have to be able to add 3 bits together, and we have to know what the sum is and what the carry is that gets generated to the next column. Theoretically, if we can do that, we can add 4 bits, we could add 400 bits. Just keep moving across. Okay, so a full adder is a circuit that does what we just did for 1 column of numbers. So here's what a full adder looks like. I'm going to draw a system diagram, and I'm going to put my inputs on the right. So I'm going to have an input A and an input B. And I'm also going to have an incoming carry. And I'm going to produce 2 outputs. I'm going to produce a sum, and I'm going to produce an outgoing carry. And so if A is 1 and B is 1 and my incoming carry is 0, my sum should be 0 and my outgoing carry should be 1. It's just doing what we do when we have 3 numbers that we want to add up, A, B, and carry in, produce this sum, produce that outgoing carry. Everybody clear on that? Now designing this circuit's not too bad. It's got 3 inputs, it's got 2 outputs. So there's 8 rows in the truth table, and there's an equation for sum, an equation for C out. So that's not going to get too bad. And there's a fair amount of things that a K-map will simplify for the carry out. The sum's kind of a pain, but that's okay. So we can build a circuit to implement this full adder. Here's what we do with this. Suppose we make the following circuit. So I'm just going to label this FA for full adder. Suppose I make 4 of these circuits. And so I'm going to feed in 2 bits A0, B0 in the top of this adder. Going to feed in A1, B1, A2, B2, and A3, B3. And I'm going to generate my sum from each block down on the bottom. And each of these generates a carry out. I'm going to take the carry out from this first adder and feed that to the carry in of the second adder. And the second adder's carry out I'm going to feed to the carry in of the third. And the third adder's carry out I feed to the carry in of the fourth. And the fourth adder's carry out, I'll just let it hang out here in space. So what's going to happen if I set A0, 1, 2, 3 to be 0, 1, 1, 0, and I set my B inputs to be 1, 1, 0, 1, and I set this first carry to be a 0, what's this circuit going to do? It's going to add A0, B0, and a 0, and the sum is going to be this bit right here. So I can call that sum 0. And if it generates a carry, that carry will be fed into the second full adder and will get added to A1 and B1. If the carry is 0, it'll do 0 plus 1 plus 1. If the carry happened to be 1, it would do a 1 plus 1 plus 1. So the output of this summer, this adder, is going to be the next bit of our sum. And then the third bits, A2, B2, will get added to whatever carry was generated from here. So we take the carry, we add these third bits, and that's going to give us this, which is the third bit of our sum. And then the fourth bits of our inputs A and B get added to whatever carry we got from that, and that gives us the fourth bit of our sum. And whatever carry we get out of that, we can just treat that as a fifth sum bit. And so this is a 4-bit adder. And it takes significantly less hardware compared to writing out the full equation for 4 bits for A, 4 bits for B. That's 8 inputs, 256 rows in your truth table, and 5 outputs. Right? This is significantly less hardware. It's whatever hardware we need to make one of these full adders, we just make 4 of them. And then you just connect carry out to carry in, feed your inputs into the inputs of each adder, take your sums and your final carry out. That's your 5-bit sum. Yeah?
What does it say, sum 4 instead of 3?
Ooh, thank you. Good. And we can extend this. If we want a 32-bit adder, we just take 32 of these things, lay them out side by side, take each outgoing carry, feed it to the next incoming carry. There's your 32-bit adder. And it takes 32 times as much hardware as you need to build one of these, which is a handful of gates. So this is a much better way, hardware-wise, to build an n-bit adder. So for the 2-bit adder that you made a K-map for, 3 K-maps for, what does this look like? Here's a full adder. Here's a full adder. We have 2-bit inputs, A0, A1, B0, B1. Initial carry in of 0. A carry out goes to a carry in. So here's sum 0, sum 1, and our final carry out is sum 2. That's all we're going to need. And that's going to be a lot simpler than the equations you came up with for a 2-bit adder. So is this making sense? It's a totally different approach to designing a circuit. Every circuit we've built so far in here, we start with a system diagram, we go to a truth table, we write equations directly from the truth table using a sum of products or a product of sums, possibly using K-maps to simplify. Here we're not doing that. We're looking functionally at what we want our circuit to do, which is we wanted to do pencil and paper addition. Add one column, bring a carry over, add the next column with that carry, and so on. And then we're building a circuit to basically do that. And the result is we end up with a simpler circuit. But the equations you get for sum 0, sum 1, and sum 2 will look nothing like the equations you got here. which is a good thing. There's one other simplification we can make here. This full adder is a circuit that takes 3 inputs. Any combination of zeros and ones produces a sum and a carry out. We'll take a look at this part of our 2-bit add circuit. Does this full adder need to be able to handle any combination of 3 inputs, 0 and 1? Looking at the way I've got it wired, what do you notice about it?
The carry is always 0.
The carry in is always 0. So it's like a full adder, but we're always connecting this to a 0. So remember, to design this, we're going to make a truth table. The truth table is going to have 3 inputs, which look like A and B and C in, and 2 outputs, sum and C out. And there's what your sloppy truth table looks like. But in the case of this first full adder, the carry in is always 0. We don't need to do any of this, because we know we're never going to have a case where Cn is 1. Well, if we know Cn is always 0, we don't need that to be an input. So guess what? That first full adder is a function of just 2 inputs. That's a significantly simpler circuit. Now the second adder, that has to have 3 inputs because we've got a carry coming in. And if we build additional adders, that's got to have a carry in also. Right? All of these need to handle either a 0 or a 1 coming in, but this first one is special. So we can build a simpler circuit here, and this is something called a half adder. And what's a half adder look like? It's that. Takes in 2 bits, A and B, generates a sum and a carry out. And that's a fair bit simpler circuit than the full adder. So the way you're going to actually implement your 2-bit adder in Lab 3 is going to look like this. Here's a half adder and a full adder. Your bits go in over here. The half adder still generates a carry out, but that gets sent to the carry in of the full adder. And then the sum out from the first one is your sum bit 0. The sum out from your first full adder is your sum bit 1. And the carry out from your full adder is your sum bit 2. And so that's going to be what you design, what you come up with full equations for, what you design a circuit for with part numbers and pin numbers, and then ultimately what you build. All right, that's a lot of stuff. Questions about that?
So a half adder is just a full adder but without a carry in?
Exactly. A half adder is just a full adder without a carry in, or specifically where you think the carry in is always 0. So it still does, you know, A plus B plus a carry in with carry in 0. So it just does A plus B. So if you wanted to write the truth table for a half adder, could you do that? Right, the inputs are A0 and B0, the outputs are sum and carry out. And you basically say, what's 0 plus 0? Well, the sum is 0, the carry out is 0. What's 1 plus 1? The sum is 1, the carry out is 1. 0 plus 1, the sum is 1, the carryout is 0, and 1 plus 0 is exactly the same thing. So it's a 2-input truth table, 4 rows. You write down the values for the sum and the carryout, and then you go ahead and find equations, simplify, build a circuit. And the full adder is almost the same, except it's got a third input, which is carry in. All right, so yes?
I was saying, like, I was thinking, instead of having just is there like an A, B, C, and D, like 4-bit addition that you can use an adder instead of just 2?
Like a full adder that takes 4 inputs?
Yeah, like A, B, C, and
D. You could. So, this is something we'll come back to, but imagine that you're building a 1,000-bit adder. So you have 1,000 of these things all strung out side by side. It's going to be really easy to build compared to other approaches, but it's going to be really slow, especially in the following case. Let's say you're taking all ones and you're adding a single 1 to it. So this is going to be 1 plus 1 is 0, which is going to generate a carry of 1. 1 plus 1 will be 0, which will generate a carry of 1. 1 plus 1 will be a 0, which will generate a carry of 1, and so on. Well, when this thing starts running, this is going to see an incoming carry of 0. It's going to do 1 plus 0 is 1, right? Because 1 plus 0 is 1 with a carry out. But eventually, this carry is going to ripple all the way down here, and it's going to say, oh, I'm doing 1 plus 1 plus 0. That's a 0, and it's going to generate a carry of 1. And this last full adder will say, oh, I've got a carry of 1 plus 1 plus 0. That's a 0 with a final carry out of 1. But your answer is not going to be correct until this 1 from your first adder ripples all the way down 1,000 of these adders. Okay, and that's relatively slow. So this is something called a ripple carry adder. Ripple carry adders are easy to design because you just keep laying out full adders side by side, but very slow. And the more bits you have, the slower they are. Well, one way to reduce the number of stages that this carry has to ripple is, instead of making these 1-bit adders, let's make them 2-bit adders. So take in an input A1, A0 and another input B1, B0. So now it's got 4 input bits plus an incoming carry, and it generates a 2-bit sum, a 3-bit sum, and a carry out. Well, if each of these takes in 2 bits of input, you've only got 500 of these super duper adders, and so your carry has less distance to ripple. It's only going to have to go half as far. That's going to be faster. But when you're done, you've got these 3-bit sums. You need to put those together somehow. So there's a whole branch of computer architecture just dedicated to designing circuits that do fast arithmetic. And there's lots of clever stuff that's been done, for example, to do very efficient addition of wide numbers. And why do we care about adding numbers? Because when you multiply, you're basically doing a lot of additions. Because how do you multiply numbers? Multiply by the first digit, multiply by the second. You get a whole bunch of partial products, and then you have to add those together. And if you're multiplying 1,000-bit numbers, you'd get 1,000 partial products and add them. And what does it take to multiply in binary? Well, one piece of it is pretty easy. Right, how do we multiply with pencil and paper? We take this digit and we multiply this number by it, and we write down the result. Well, multiplying this by 1 is easy. You just get the original number. Uh-oh, here I got to multiply by 0. Well, that's pretty easy too. You're just going to get 0. There's another 1 I got to multiply by. Is that a problem? No, I just get the original number. So getting these partial products is really fast. It's either 0 or it's the number that you're multiplying. And all your work comes in doing this addition. So a lot of research in fast multiplication comes down to doing fast addition. So that's one way to do it, is to have full adders that basically do more than just one bit. And we'll talk about some of these clever approaches if we have time at the end. We'll talk about things like Wallace trees that are really smart ways to do addition and multiplication. Carry look-ahead adders, things like that. All right, other questions, comments? So I'm still not gonna start in on lab 3 yet, but I'm gonna take a peek. I'm pretty sure oh, never mind. I'm looking at lab 4. Oh, you're way ahead of the curve. All right. So when we get to this lab, what you're going to do is you're going to build a circuit that uses, have you seen those little dip switches sitting in your parts box? So they look like this. Right, and sometimes they have little slide switches on them. Sometimes they have little rocker switches that you push down one end or the other. But they're basically a really simple switch that lets you close a connection or leave a connection open. So when we build our 2-bit full adder, we're going to use a block of switches like this for our input. And typically you're going to take 2 switches over here to represent A and 2 switches over here on the other side to represent B. And if they're down, that's a 0. This switch here, which is up, that represents a 1. So if I want to do 2 plus 2, I would slide this switch up, and I would slide this switch up. That's 1, 0 plus 1, 0. And it should give an output of 4. And right now, those switches are down, those switches are down. It's doing 0 plus 0. It should give an output of 0. Well, how do we display an output? We could have 3 LEDs. And this could be bit 0, 1, and 2 of our sum. And so if the sum is supposed to be equal to 3, you'd expect this LED to be off and these 2 LEDs to be on. And you'd say 0, 1, 1, that's a 3. And so you're going to put 3 LEDs into the output of your circuit to make sure that it's adding correctly. But we're going to do something even cooler after that. We're going to use a 7-segment display. Don't want great deals. So it's going to be this thing that looks like this, and each of those lines, horizontal and vertical, is a little LED. And we can make it light up or we can leave it dark. And the idea is by lighting up some of these LED bars, we can make this look like a digit or a letter or just some random symbol. So this display looks like this. And if we generate the right signals to light up this, and this, and this, it's a really sloppy 7-segment, it's going to display this, which is going to look like a 7. Right? And if we light up a different set of these, it's going to look like a 6, or a 5, or a 4, or a 3, or a 2, or a 1, or a 0. Or we could do an 8, which is every segment, or we could do a 9. And so you're also going to include in your circuit whatever you need so that when you produce your sum with your add circuit, it drives a display like this so you can actually see the digit, which represents the sum. So now if you set your inputs to be 2 plus 3, your display should look like this, and you can look at it and say, 2 plus 3 is 5. And there's circuitry that we'll talk about in a week or two that does this decoding for you, so that if you feed it a binary 5, it would do whatever has to be done to make that display something that looks like a 5. That's something that already exists, and they're in your parts box. It's called 7447. So you're not going to have to build anything extra to do that. All right, questions? So this is our first foray into doing arithmetic with digital circuits. And we don't really go beyond addition in this course. In a third or fourth year or a graduate level course on digital logic, you would look at building multipliers and dividers and things like that. We will talk about subtraction, but we'll talk about subtraction in terms of 2's complement. But we're not quite there yet. All right, let's look at a half adder. Since we're going down this track anyway. So 2 inputs A and B, 2 outputs sum and carry out. So what is 0 plus 0?
0.
Pop quiz, good, 0. So that means the sum bit is 0 and there's no carry coming out. What is 0 plus 1? 1, and there's no carry generated. 1 plus 0 is exactly the same thing. And then 1 plus 1 is 2, so that's a 0 with a carry out. There's a truth table for a half adder. So if I wanted to write an equation for carry out in terms of A and B, anybody see a good equation?
A and B.
It's a straight AND gate, A ANDed with B. 0 in every case except when A and B are both 1. There's your carry circuit, it's just an AND. How about the sum? We want a 1 if A is 0 and B is 1, or if A is 1 and B is 0. There's our K-map. Say again? Almost. That's an XOR, right? Checkerboard. And since we only have 2 terms and we've only got 2 inputs, it's not too bad to just write the equations for this. This rectangle would be A, B bar. This rectangle would be A bar, B. So the equation is sum equals the sum of those 2 product terms. But if you recognize it, that's an exclusive OR. And from the original truth table, you can see that the output of the sum is 1 if exactly one input is 1. So that's an OR, that's an OR. But if they're both 1, the sum is 0. So half adder is 2 gates. An AND gate to get your carry out, an exclusive OR gate to get your sum. If you have an XOR gate. If you don't have an XOR, then you need 2 AND gates and an OR gate to build it. But we have XORs in our parts boxes, so you get to use an XOR. Okay, full adder is slightly more complex, but really not too bad. We have 1 more input carry in, so we have 8 rows. And we still have 2 outputs. The sum is going to be a bigger checkerboard, so it's going to be a more complex exclusive OR. But we'll figure that out when we get there. And the carry out's going to end up being 3 ones, so, or 3 terms when we reduce it. So it's not too bad to build. You ready to change gears?
Real quick, is this gonna be on lab 3 or 4?
This is actually lab 4. So, for some reason I thought it was lab 3. So, but lab 3 you totally could have done. But we'll take a break to solidify the background anyway. All right, change of gears. This will lead us into Thursday. Theory versus reality. So most of what we've been dealing with has been theoretical. We were talking about zeros and ones, and if you put 2 ones into an AND gate, the output is a 1. That's all a very kind of idealized view of the world. In practice, these AND gates are physical circuits. And we don't actually feed in a 1 or a 0, we feed in a voltage. But if the voltage is close to 5 volts, it's treated like an input of 1. And if the output of our AND gate is close to 5 volts, we treat that output as a 1. But in reality, the output might be 4.625 volts. But if we feed that into another gate, it's going to say, yeah, that looks like a 1, and it'll treat it like a 1. But there's these differences between theory and reality. So here's another difference. Let me draw a circuit here, which is just an inverter. A goes in, B comes out. And let me draw a graph where we have time going horizontally. And vertically, we're going to have the voltage of A. And let's draw the corresponding voltage of B. And if A changes from a 0 to a 1, B will change from a 1 to a 0. I'm going to draw this dotted line to show that those things are lined up. So A is 0, B is 1, A is 1, B is 0. Okay, that's the idea. That's not what happens in practice. And we saw this a little bit when we were looking at square waves on the oscilloscope and changing the frequency and blowing it up. For one thing, B does not drop directly from 5 volts to 0 volts. It falls over a little bit of time and eventually comes down to 0. But that's not too big of a concern because we've got this clear idea that once it gets down below something like about 1 or 2 volts, we're going to treat it as a logic 0. But here's the other thing that happens. Even if we ignore this gradual drop-off, in practice, it takes some amount of time for B to respond to that change in input. So at this point, A went from a 0 to a 1, but for some period of time afterwards, B was still a 1. And then eventually the circuitry got around to responding and said, oh yeah, my output's supposed to be a 0, and the output went down to a 0. But there's some brief instant where the output of the inverter was not the opposite of the input. During this time window, the input A was 1, the output B was also a 1. This is just a physical reality. When you flip the light switch from down to up, do the lights turn on instantly? They look like it, but they don't. Because electricity has to flow up to the bulb, and if it's an old bulb with a filament inside, that filament has to heat up, and it starts emitting photons, and those photons have to leave and travel through space and get to your eyeball before it looks like the lights have turned on. It's tiny, but it's still non-zero. So there's a moment where the light switch is on, but the room is still dark. That's what this is. Now for us, turning on a light in a room, that's not a problem. We're not going to stumble in and trip on something because the lights took too long to turn on. But for a computer, this can be a huge problem because in this tiny amount of time, lots of things can happen. Right? It can get all the way into the room and it can smash into the back wall and break through it and stumble into the driveway before the lights have turned on. So this is a potential issue. So this is called a propagation delay. And how bad is a propagation delay? Well, go to your website, look up component specifications. Let's look at an inverter, 74LS04. So there's the picture of it. And again, if you're looking at these data sheets, make sure that the picture you're looking at matches the part you have. If you have a 74LS04, which is right here, this is the picture. This is a different kind of part down here. That's a 5404. So there's the truth table, high goes to low, low goes to high. There's a picture of what it looks like, 6 of these triangles with circles on the end. There's what's actually inside, resistors and diodes and transistors. So if you wanted to build one on a desert island, you could scrounge these parts and build your own inverter. And then there's a section called switching characteristics. So TPLH, that's propagation delay from low to high. That's saying if your output is low and now it's going to go high, how long does it take? You're going from an input to an output. Typical time, 12 nanoseconds. Maximum time, 22 nanoseconds. That's a lot of time. 22 billionths of a second. If you have a CPU running at 4 gigahertz, it's taking a quarter of a nanosecond for a clock cycle. So 88 clock cycles before this inverter generates the correct output. And your CPU can do a lot of stuff in 88 clock cycles. So if you built a circuit and connected it to your CPU and it was built with one of these gates that takes 22 nanoseconds to respond to the input, you're going to get some weird stuff. This is what happens when you overclock your CPU. How many people have overclocked their CPUs? You can admit it. I won't tell the warranty people. When you overclock, right, you're saying I want things to happen faster and faster and faster, but the circuitry inside can only respond at a certain rate. It's a lot shorter than 22 nanoseconds because the distances are smaller, the voltages are lower, but there's still some maximum speed that these gates can respond at. And if you run the clock too fast, you're trying to do things before what you did after the last clock tick has fully caught up. And up to a point, that works fine. Beyond that, you start glitching out a little, and beyond that, things aren't doing the right operations logically anymore, and usually your CPU crashes. The bigger danger, of course, is heat. The faster you clock, the hotter things go, and that's why you have, liquid nitrogen cooling your CPU or dry ice or something. And usually your CPU might overheat and sometimes actually like smoke or flame before you actually get into performance problems. And this is always present, right? There's always a propagation delay, and sometimes we can ignore it, right? When we're building a 2-bit adder and you're going to flip the switches and see what the output is, we don't care how long it takes. I mean, if it took 5 minutes, that would be a problem, but if it takes nanoseconds, milliseconds, we don't care about that. Sometimes we're actually going to take advantage of this propagation delay. When we start talking about memories, we're going to use this to make some things work. But then sometimes it's really critical, and when we start designing basically computer circuit state machines, we'll have to talk more about propagation delay. All right, that's a whole armful of stuff to ponder. So we'll continue from here on Thursday.